Good evening, everybody, and you're all very welcome. Those of you on the call this evening and those that will be joining in the future on our YouTube channel. If you logged in earlier, you would see that our November meeting, we've got Noel Castro Segura from Warwick University, and he'll be talking to us about binary stars and stellar cannibalism. He's titled his talk. Evidently, some binary stars have transfer mass between each other, which was new to me. The October meeting is in fact on the last day of September because there is a bit of a need to have some Monday meetings. So that'll be next. The October meeting will be 30th of September, and we're visiting the Amateur Radio Astronomy Centre in Portugal. And they do a whole range of observations. So that would be really interesting. I mentioned earlier in our chat that next year sees the European Amateur Radio Astronomy Conference coming to the UK, beyond the Harwell campus. And I think it's going to be a very interesting weekend. So if you haven't signed up and registered an interest at this stage, then do visit our website. It's eucara.org. And at this point, we're just wanting to gauge how many people are likely to turn up. It'll just help with the planning. And tonight, I'm very pleased to welcome two early career scientists that were recommended by their supervisor. So the expectation was already built quite high. And Johnny Pearce and Luke Holden are joining us, both now at Hertfordshire University in the School of Physics. And I believe it's Luke that's going to kick off.
Yeah, well, thank you very much, Paul. Thanks for everyone for having us here. It's really good. So we're going to be doing like an AGN night tonight. So for those of you who don't know what an AGN is, we're going to go over that. That's an active galactic nucleus. So we're effectively talking about supermassive black holes and the impact that they have on their surrounding galaxies. I'll first kick things off talking about some observations I did as part of my PhD last year in a paper that was published earlier this year with the Atacama Large Submillimeter Array, or ALMA, in Chile, looking at molecular gas accelerated by supermassive black holes. And later on, Johnny's going to talk about some of the work he's done with the low frequency array, or LOFAR, at his time at Hertfordshire. So to start off, as the title says, Dr. Luke Holden. I put that on there because as of Monday, I was awarded my PhD in astrophysics from the University of Sheffield. And, you know, I spent 3.5 years doing this PhD, so I want to get my worth out of it. And that means putting doctor at the start of everything I possibly can. And this is my first opportunity. So that's why that's up there. So yeah, as I say, I'm now at the Centre for Astrophysics Research, University of Hertfordshire, as is Johnny. So we're looking forward to showing you some of the research we're doing and maybe some of the directions we're going to be taking it in the coming years. To kick things off, I want to place the context of everything we're going to be talking about today in the context of galaxy evolution. And that hopefully will demonstrate to you all why what we're doing is important and why you should care, right? So to be very clear, when I'm talking about a galaxy, I mean a big collection of stars and gas and things in space. Effectively, the way the universe is structured is you have these things called galaxies, typically thought of these spiral disky things that contain gas and stars. Then you have a whole load of void and space, then another galaxy, you have groups of galaxies, and it goes on. When I mean galaxy evolution, or I talk about galaxy evolution, what I mean is how have the properties of galaxies changed since the Big Bang, since the start of the universe? So over the past 13.5 billion years, how have the stars in the galaxies changed? How have the star formation going on in the galaxies, how has that changed? How has the properties of the gas in galaxies changed? It's really important that we establish answers to these things because everything that we consider, or almost everything we consider in astrophysics, happens inside galaxies, right? So we have, for example, star formation. That depends on the properties of the gas in galaxies, which again, as I've said, depends on how the galaxies have evolved over the past 13.5 billion years. The properties of the stars as they form affects how they evolve. So studies of stellar evolution, for example, need to be placed in a context of galaxy evolution. Planet formation as well. That's a particularly interesting one, because if it wasn't for planet formation, we wouldn't be here. And to understand planet formation, we need to understand how the gas which form planets, how that's changed over the history of the universe. And of course, more exotic physics. So physics, or things that give us insights to the universe in really unique ways, where we can probe really extreme conditions, like around, for example, black holes. Again, these things almost only exist in galaxies. So it's really important that we understand how galaxies have changed and evolved over the duration of the history of the universe. Now, as observational astrophysicists, when we look out into the universe, we see that a fraction of galaxies have something weird going on. So you see two such galaxies here, and we see in the centers of these galaxies, there are these really bright, compact regions. Now, we call these really compact regions, really bright, compact regions in the centers of some galaxies, active galactic nuclei, or AGN. These things are so bright that they actually outshine the combined light from the rest of the host galaxy. So if you add up the brightness from all the stars in the galaxy, it is less than the brightness produced by the AGN, this compact region in the center of some galaxies. So you can see there, just to point out, that's what I mean when I'm talking about the AGN, these really compact regions. Now, what's powering these? Like, why do we have this incredible amount of energy being produced in a very small region in the centers of galaxies? Well, we think what is happening is effectively accretion onto supermassive black holes. So by supermassive black holes, I mean black holes that have masses that are 1,000,000 times greater than that of the sun. We think now that almost every galaxy has a supermassive black hole in its center. And as gas is eaten or is fed onto that black hole in a process that we call accretion from the surrounding galaxy, if that accretion happens under certain conditions, effectively you can have some really weird things going on. So first of all, as that gas falls around or towards the black hole, it first forms a disk around it, in which you have a constant inflow of material onto effectively the surface of the black hole. We call that an accretion disk. Now, again, under these certain accretion conditions, when this accretion happens in a particular way, what we believe happens is that dynamical friction in that disk, because you have a whole load of material in the really extreme gravitational conditions, lots of effectively friction, it heats that material in the accretion disk up to really high temperatures. We're talking here millions, if not billions of degrees, right? Because this stuff is really hot, it becomes what we call ionized. So you start stripping electrons from the protons in this material. So it has an electric charge, and it also has a magnetic charge. But the key point here is, because this stuff is really hot, it is also really, really bright. And this is the source of the brightness that we see at optical wavelengths, so at visible wavelengths that we see with our eyes. That's the source of that radiation, or that brightness that I showed you in the previous two photos. So we have these supermassive black holes with accretion disks going around them. Those accretion disks get very, very hot and very, very bright. Now, because we have really strongly magnetic and electrically charged material around the vicinity of a supermassive black hole, in which you have really crazy gravitational physics going on, effectively what happens is the magnetic fields from that magnetized material in the accretion disk get spun up along the direction the black hole is spinning in, because these black holes we think spin. And in doing that, the magnetized material in the accretion disk effectively gets launched along the spin axis of the supermassive black hole. And the end result of this is a really highly collimated, or really tight launching of plasma, so charged magnetic material, at speeds of a fraction of the speed of light, which is incredibly fast, away from the supermassive black hole. And we call these things jets. These jets can extend on really small scales, which is what I'm going to be talking about today. By small, I still mean very, very large, but really just in the central regions of galaxies, out to really, really large scales. So well beyond the extent of the galaxy itself. And that's the sort of thing that John's going to talk to you about later with some of the work he's done. So put all this together, and we call this system an active galactic nucleus, or an AGN. So an AGN, what I'm talking about, is a supermassive black hole which is accreting material. That material becomes very, very hot and becomes very bright. And it also launches this collimated stream of very, very fast plasma that we call a jet. So the interesting thing here from a radio astronomy perspective is that jets are very, very bright at radio wavelengths. This is because of a mechanism called synchrotron radiation. Johnny's going to talk about this a bit later, but effectively this is just when you have charged particles spinning or rotating in, or rather spiraling along magnetic fields, in which you get this emission that produces photons or particles of light at radio wavelengths. So as I said, these things are incredibly energetic. They're actually the most energetic continuous phenomena in the universe, right? There's an idea that, okay, if every galaxy we think has a supermassive black hole in its center, and if that supermassive black hole can turn on and off in this way, having these phases of AGN activity in which it, the accretion disk becomes incredibly bright and you start getting these jets produced. If you can somehow impart some of the immense energy produced by one of these events into the gas of the surrounding galaxy, you might really drastically alter the properties of the surrounding galaxy. For example, you may heat up or remove gas which you need to form stars, and therefore affect how the galaxy forms stars. Okay, so we now think that these AGN are an incredibly important part of galaxy evolution, in that they prevent star formation and effectively stop galaxies from forming new stars. Now, there are many ways that we think they do this. Johnny's going to talk about one of the ways. Today in my talk, I'm going to focus on something called AGN-driven outflows. So by an outflow, what I mean is effectively bulk motions of gas that has been accelerated in some way by an AGN up to thousands of kilometers per second in velocity. So incredibly fast-moving gas accelerated by an AGN. And broadly speaking, there are sort of two ways we think AGN can do this. So one is via this phenomenon that we call radiation pressure. So in physics, if you have light incident on the surface, so for example, now I'm in this room, I have a lamp over there, I actually have a candle on here making the room smell nice. The light from these two sources is actually being imparted on me, and that light imparts upon me a momentum and is actually in effectively a negligible way pushing me away from them. Okay. Now, day-to-day life on Earth, that effect, which we call radiation pressure, is practically zero. It has no real effect on everyday life. When we're talking about the brightest continuous things in the universe, all of a sudden, that actually is a really important effect. So you have gas around one of these AGN systems, and the radiation or the brightness produced from the accretion disk of one of these AGN is imparted on that gas and accelerates it away up to thousands of kilometers per second in velocity, so incredibly fast. We also have these jets that I talked about, these really fast-moving streams of plasma accelerated away from supermassive black holes in AGN. We think that effectively, or we see actually now, there's good evidence for this, that these jets impact the gas in the host galaxies and accelerate that gas away, effectively like a piston being driven into some gas, which again accelerates it. The upshot in both cases is you end up with gas accelerated by an AGN up to thousands of kilometers per second in velocity. And what we think this can do is accelerate gas away from the central regions of galaxies and therefore prevent that gas from forming stars. So you're hindering star formation in the central regions of galaxies with these mechanisms. So we've known about these outflows for, I'd say, the best part of 50 years now. We've really started our investigation of them in the past, say, 20, 30 years. Now, the vast majority of studies of these outflows are done with optical light telescopes. So by an optical light telescope, I mean what most people think of when they think of a telescope, right? Effectively, a big mirror that focuses light, and then you have a camera that takes a picture of that light or captures that light, and you do things with it. So for example, here would be the Very Large Telescope shown there on the left in Chile, or the VLT. As a side note, it really is called the Very Large Telescope. I'm not bigging it up. The successor to that telescope is now being built in Chile, which is called the Extremely Large Telescope, because we're all really creative with our names. So many studies of these outflows driven by these AGN are done with optical telescopes like the Very Large Telescope. So you see here, for example, on the right, this is a galaxy that I have worked on. And this is what you see kind of in optical light. with the sort of light we see with our eyes. This is kind of what we see, and we can trace the outflows in an object like this with optical telescopes. Indeed, the vast majority of studies over the past 20 years or so have used these optical telescopes. Now, that's a really important point, because while we now routinely detect these outflows of gas accelerated by AGN with optical telescopes, what we are tracing here explicitly is ionized gas. So just the way the physics works out, at optical visible wavelengths, what we see with our eyes, you are only seeing gas which is being ionized. So that's gas at temperatures above, say, 10,000 degrees. Okay. So for this galaxy in particular, there have been studies using the Very Large Telescope tracing outflows of ionized gas accelerated by the AGN in this galaxy. Now, the kicker is those outflows in this case aren't very powerful. And by that, I mean, we don't think those outflows are having enough of an impact on the galaxy itself to affect how that galaxy will evolve. But as I mentioned, we're tracing here ionized gas, so effectively really hot electrically charged gas. If instead we were to look at radio, or technically submillimeter wavelengths, we can start tracing different types of gas that may be outflowing. For example, or in particular, molecular gas. So the way this works out is molecules, or certain molecules, emit light at radio frequencies. So maybe here we're not getting the full picture because we're only seeing one type of outflowing gas. So we can use radio instrumentation to trace other types of gas and see if that's more powerful and having more of an effect. So in this case, what we did is we looked at this object, which, if I go back, has a catchy name of 4C1250. Again, this is an object in which we know that our outflow has been accelerated by an AGN in its center. Those outflows have only been detected in ionized gas, and they're not very powerful. What we've done is looked at this object with ALMA, which is the Atacama Large Millimeter / Submillimeter Array. So this is a big array of dishes ranging in size from 12 to 7 meters in aperture, separated by 150 to 16 kilometers. So this is an interferometric array. So that means effectively you use at least 2 dishes to interfere the light to get an interference pattern. And from there, you can reconstruct an image on really small spatial scales. So you can get into a lot of spatial detail with this. And again, those distances between 2 dishes, we call a baseline. That can be with ALMA anywhere from 150 to 16 kilometers. There's 66 of these dishes in total. And with ALMA, we're looking at frequency range of about 35 to 950 gigahertz. So I respect that to many people, this would not be considered strictly radio astronomy, right? Because that's probably too high frequencies. It's more like millimeter or submillimeter astronomy. I still think it is effectively radio astronomy, but if you're one of those people that disagrees with me, that's fine. I'm going to be talking about some strict radio astronomy in a minute, so stay with me. So, as I said, with ALMA, we can revisit this object where we see these outflows in the ionized gas, and we can actually detect outflows in molecular gas and try and get a full picture of what's happening in this galaxy. Just to give a quick idea of how ALMA works for scientists like me who use it to do analysis, effectively we have ALMA observing a target. So it points how many dishes we require at a target, and we do a whole load of complex analysis, which I think is some mix of science and black magic that I don't really understand because it involves a lot of really advanced mathematics to reconstruct an image. Now, the way these images work is effectively we get what we call a data cube. So this is actually almost a 3-dimensional image where we have on kind of like X and Y, or left and right, up and down. We actually have the distribution of brightness in the field of view of the telescope. But we also have this additional axis, meaning we can see the emission of the molecular gas in a galaxy or in an object at different frequencies, which correspond to different velocities. So you can see here in the middle, this is just one of those velocities so that we are seeing a galaxy. So you can sort of see this sort of curve. This is actually a spiral arm of a nearby galaxy. And this allows us to trace the emission of molecular gas at different velocities. So we can see how much stuff there is, where it is, and at what velocity it's moving, which for us looking for, fast moving gas is really, really useful. So to demonstrate this for every pixel in this data cube, we have something like we see here on the bottom right, which we call a spectrum, where effectively we can see how much flux or brightness there is at a given velocity for every position. So we can look for signs of outflowing gas and various other things. So what have we done? So on the left there, we have the image I showed earlier. This is a optical telescope image from the Very Large Telescope. Again, visible wavelengths that we see with our eyes. This is kind of what we'd see. With ALMA, a few years ago, we got some observations of just the center of this galaxy, round near where the AGN is, where we expect to see these outflows, right? So these two plots I'm showing here on the right are zoom-ins of the center of this galaxy in molecular gas emission. So these are the ALMA observations where we're seeing the molecular gas. So the center plot here, effectively what we have is a 2D image of the brightness distribution in the central regions of this galaxy. So we see there's this really bright stuff. So the brighter stuff here is the darker stuff. The brighter stuff here is in the center, and it gets gradually fainter as you move away from the center. That makes sense, given that we know there's a very, very bright AGN there in the center illuminating the molecular gas. So it makes sense that we're seeing this distribution pattern. On the right, what we have is what we call a velocity map in the central region of this galaxy. So on the same spatial scales, right? What this essentially is showing us at every position how fast is the gas moving. So here, if the color is more blue, if it's darker blue, it means the gas is moving faster, but towards us. If the gas is red, and the redder it gets, it means it's moving faster, but away from us. So we're able to see in the relative to the center of this galaxy, how fast is this gas moving, and is it moving towards us or is it moving away from us? So we see, first of all, a very clear pattern from left to right, from blue to red, which means on the left side of this galaxy, you have gas moving towards us. On the right side, you have gas moving away. Now, this is a very clear indication that we have a rotating disk of gas in the center of this galaxy, which is interesting. Because I should have mentioned, actually, this galaxy is technically two galaxies colliding and merging. That's important because work that Johnny has done in the past has shown that we think these AGN, these supermassive black holes that become really bright, that process is triggered when you get two galaxies merging together. So as we're going back to this point, as you see here, gas moving towards us, gas moving away from us, that's characteristic of a rotating disk of gas. So what's that showing is, despite the fact that we have two galaxies merging and throwing gas everywhere, quite quickly that gas is settling down into a rotating disk. But also what we see, right in the center of this galaxy, marked by the white cross, if you can see that there, is this little blob of red stuff. That red stuff there means the gas is moving away from us quite fast. This little blob of red stuff that doesn't seem to follow this pattern. So if we were just seeing a regular disk here without anything weird happening, the division between the blue and red parts of the disk, so the stuff moving away from us, stuff moving towards us, that would be a straight line. But you can see there's this little blob of red stuff extending into the blue region. What that's indicating is we have something that isn't part of this rotating disk happening right in the center of this galaxy, right where the AGN is. Again, that white cross there. So we need to look into this in a bit more detail to see what's going on. So what we do is effectively we extract the brightness just from a line. I'm not sure if you can see my mouse here, but this is a line effectively going perpendicular to the direction of this disk, kind of going left to right across this image, intersecting the center across there. And from that line, we effectively extract the brightness at each position. So we have here what we call a position velocity diagram. So I know this looks a little bit complex, but I'll walk you through it. Effectively on the x-axis, so horizontally, we have the distance from the center of this galaxy, from the AGN, along this line which goes across the disk, right? And then on the y-axis, so up and down, we have how fast that gas is moving. Here, if the velocity is positive, that means the gas is moving away from us. If it's negative, it means it's moving towards us. And then the darker a point of this diagram is, it means there's brighter emission there. So what this allows us to see is effectively at a given distance from the center of this galaxy, how fast is gas moving and how much of it is there, or how bright is it? So there's quite a few things going on there. First of all, we see this very bright emission. So brighter emission here is the dark parts of this diagram. This very dark emission, sort of, you see our mouse again here, just left, top left and bottom right at the center, which seems to follow this almost like curve pattern. Now this is exactly what we'd expect from our knowledge of gravitational physics. This is exactly what we'd expect to see for a rotating disk. So that confirms that what we're seeing in this galaxy is a disk of gas which is rotating under gravity. These blue contours here are a simulation that I ran, which is fitting a model of the disk to the emission from this data. So effectively, that covers a rotating gas disk. And this is really nice because basically anything that falls out of these contours or significantly far away from these contours means that that emission away from the contours isn't actually rotating, right? Because those contours are effectively covering the rotating gas in this object. So what that means is we see some of this other emission here, particularly there's a quite dark yellow patch kind of at the position of the nucleus, so 0 on the horizontal axis. Just above here, there's this blob of emission moving with velocities between 400 and 600 kilometers per second away from us, which we can see here is significantly higher than the velocities of this disk. And that's indicating we have something interesting going on here. So just to highlight that, we think this is an outflow. So effectively what we're seeing here is at the position of the AGN object right in the center, we are seeing some gas moving at 400 to 600 kilometers per second in velocity, which is much faster by several hundred kilometers per second than the rotating disk, indicating that we have the AGN in this object, the supermassive black hole, accelerating molecular gas away from the central regions up to velocities of like 400 to 600 kilometers per second. So that's really interesting. So basically what we're seeing here is with ALMA, we have detected a supermassive black hole accelerating molecular gas away from the central regions of the galaxy. So maybe let's look into this in a bit more detail and see if we can tie down how exactly is this supermassive black hole or this AGN doing this. So what we have here is a 2D map. This is just a 2D image of this outflowing gas. So effectively here, we are only looking at the high velocity emission. So emission between 400 to 600 kilometers per second. So ignore the blue stuff for now. Just look at the brown and orange stuff. Here again, darker colors or darker brown, dark orange corresponds to more emission, brighter emission at high velocities. So you can see in the center of this, there's this bright or dark, brown blob. That is the position of the outflow. So that's showing you in the image kind of where it is. Now, what we can do is we can take radio observations taken at a frequency of 6 gigahertz with several radio telescopes with a technique called very long baseline interferometry, which you may be familiar with, or VLBI, to image the plasma jet being produced by this AGN. So they're the blue contours here. So to briefly explain how we get that image, effectively we have some radio telescopes, I believe in this case in the Netherlands, and we also have radio telescopes in the USA, so the VLA, if you're familiar with the VLA, and we use those two effectively as a very largely separated interferometer, and that allows us to recover the emission from this radio plasma on really small spatial scales, and that's how we're able to see the shape of this AGN jet in detail here. So here, just to be very clear, the jet are these blue contours observed with very long baseline interferometry, and the dark brown blob is the outflow of molecular gas that we detected with ALMA. And we're seeing how the two positions line up with each other. Now, the interesting point here is you can sort of see this jet has a kind of kink to it in the south, so to the bottom. So again, the white cross here is the central position where we think that the black hole is. South of that or below that, you see the jet comes out straight and then kind of turns. So something is causing this jet, it seems, to be deflected. So what we're thinking happens here is effectively the plasma from this jet, or in this jet, is going out straight, and then after a while, it is hitting a particularly dense cloud of gas, which then deflects the jet sort of downwards. Interestingly, and this is why we think this is happening, you'll see that the position of this bend in the jet corresponds to the position of the molecular outflow. So this builds up this picture of what we think is happening is that the jet is being launched away from the supermassive black hole as part of the AGN. It's hitting a dense molecular cloud and being deflected. And in the process of doing that is accelerating molecular gas away. So we think we're seeing here very clear evidence for a plasma jet from an AGN accelerating an outflow of molecular gas, which is really interesting because molecular gas is effectively the stuff that forms stars. So what we're seeing here is that these jets produced by these AGN or these supermassive black holes are removing and accelerating away gas we need to form stars and potentially affecting how this galaxy will form stars in its central regions in the future. So let's bring this back all together and maybe place this in some broader context. As I mentioned before, this particular object, this particular galaxy, had been previously observed at optical wavelengths or visible wavelengths with the Very Large Telescope. And again, due to the way the physics works out, these telescopes or the optical telescopes are tracing ionized gas with temperatures of above 10,000 degrees Kelvin. So these previous studies that looked at this ionized gas with these optical telescopes found that the ionized gas which is outflowing in this object is carrying away about 11 solar masses worth of material every year from the central regions of the galaxy. So by solar mass, I mean the mass of the sun. So effectively, the ionized gas being accelerated by the jet, the AGN jet, and this object is carrying around 11 solar masses per year away from the central regions, which actually isn't enough, we think, to impact how this galaxy would evolve. Interestingly, and very, very importantly, with our ALMA study, looking at the molecular gas, which ALMA allows us to do, we see instead that the molecular gas, which is accelerated by this jet, it is carrying 20 times the amount of material that the ionized gas is. So you can see here the mass outflow rate, so how much stuff is being carried away every year, is around 200 solar masses per year, which is significantly higher, and we think indicates that this is having a significant impact on how this system will evolve over the coming billions of years. So the key point here is, if we hadn't have looked at this object with ALMA, with our radio observations, we would have been missing a significant and crucial important part of this outflowing gas, and we would have completely misinterpreted the impact this AGN is having on its host galaxy. Because if we only looked at the ionized stuff, we'd have thought, well, this AGN isn't really impacting how what the gas is doing. But with ALMA, that allows us to see that actually, yes, most of this mass is in the molecular gas. So, and most of that, and that molecular outflow is going to have a significant impact on how the galaxy evolves. So it shows that we really need to use observations at different wavelengths and frequencies, particularly radio observations and sub-millimeter observations like with ALMA, to recover the full picture of how these AGN are impacting the host galaxies and how they're affecting how their galaxies evolve. So just to sum up my part of the talk, using the Atacama Large Millimeter/Submillimeter Array, or ALMA, we've discovered molecular gas in the center of a galaxy, which has been accelerated by the plasma jet produced by an active galactic nucleus. So an active galactic nucleus, or AGN, again, is an accreting supermassive black hole in the center of a galaxy. And these jets are when that mechanism launches these really fast streams of plasma away. We think in this case, one of those fast streams of plasma, or the jet, is hitting a molecular cloud and driving away gas in a way which is going to have a significant impact on that galaxy going forward in terms of how it forms stars. And importantly, this molecular gas seems to be carrying much more mass and is therefore having much more of an impact on the galaxy than the previously observed ionized gas, which you trace or observe with traditional optical telescopes. So this really shows the importance of radio observations in these kinds of studies. So I'll just leave that up there with my contact details. If you have any questions, I think, Paul, we're going to do some questions now or maybe at the end after Johnny's talk. I'm not sure how you want to structure that. But outside of this session, or if you're watching this on YouTube, hi, you can get in touch with me either at my email address, or you can follow me, ask me some questions on Twitter or X or whatever it's called these days. And if you want to find out more about me and the work that I do, you can go to my website there. So thank you very much for your time and attention. It's been great being here. So thank you.
Thank you very much, Dr. Holden. We will take questions at the end, I think.
Fantastic.
And if you think you might not remember your question, then put them in the chat. Okay, thank you. Thanks very much.
Thank you very much. Thank you.
Could do some now if you wanted, so that people don't forget while it's still fresh. Or if you'd rather do them at the end, that's also fine. And yeah, up to you. Yep.
I mean, yeah. So if that's for you, Paul, I'm not sure how you'd rather do it. If you'd rather do things at the end or do it now, I mean, I'm happy either way.
Yeah, let's do things at the end. Otherwise,
cool.
Time might run away with us, and I don't want that to happen.
Yeah. Sure, no worries. Okay.
Thanks, Luke. I think if you stop sharing, I can get mine started. Okay. Okay. You all seeing that all okay?
Yeah, that's fine.
Yeah, good. Right. Yeah, thank you for the invitation to do this. It's nice to talk to a group of interested astronomers in Amateur Astronomers Association. Yes, so as Luke mentioned, we're now, funnily enough, at the same university. We are now both doctors as well, which is something new since we were invited to do this talk. And today I'm going to kind of follow on from what Luke was talking about and give a sort of broad overview of the low frequency array radio telescope and what we do to study AGN with it. Okay. Yeah. Okay, so as Luke touched on a little bit, we have a lot of sources of emission that come from active galactic nuclei in the middle of galaxies from this area near the supermassive black hole. And one of them is the radio jets. So these happen semi-regularly, and here is an example of what something like that might look like. And the emission that we get from those jets actually comes out in radio wavelengths via the synchrotron mechanism, which is something that Luke also introduced. So this is what happens when you have a charged particle spinning around a magnetic field line. It essentially, because it's accelerating, changing direction, it sends out radio waves in this way. And you may wonder why we want to look at low frequencies to do our radio AGN studies, so AGN with jets. And it's because the synchrotron emission that comes from these is actually brighter towards lower frequencies. It's just the way that the brightness of the emission, which is on the y-axis of this plot here, varies with the frequency. As you go lower, this slope increases, you get brighter, essentially. Just how this mechanism works. So you may think, imagine all the nice AGN science we could do if we were to look down there. And, oh, well, that's handy, isn't it? So we built this radio array, a low frequency array, specifically to look at this type of thing. So this object you're seeing in the middle of the screen here is what we call the superterp. This is the center of the low frequency array. You can see several stations of antennas here, all grouped together. And this forms part of the low frequency array. And I found out today, actually, that terp is actually a local term for a sort of raised area on which to build something to protect it from water. So that's a local thing in the Netherlands and where this array is built. Okay, so we have a the low frequency array. This is what we call a phased array that operates at frequencies below 200 megahertz. So a phased array is basically these antennas that we have collecting the signal are not steerable. And what we have to do is essentially add in some signals to the electronics to point the telescope into certain directions on the sky. And that's something I'll touch a bit more on later. So we have these two different components in each station. We have low band antennas, or LBA. These operate at 10 to 90 megahertz. We have high band antennas, which operate just above the FM band in the radio at 110 to 240 megahertz. We've got a large fractional bandwidth, so it's a sensitive instrument. It's got flexible spectral resolution. We can change how much of frequency of a region of frequency we collect signals over quite easily. There's a very wide instantaneous field of view, which means you can get an image of a wide part of the sky. It has multi-beaming capabilities. You can point at different regions in the sky at once, and it also has flexible angular resolution because of how the array is structured, which I'll talk more about later. But because Paul mentioned that you have quite a few people in the audience who are former engineers and may be interested in the technical side, I thought I'd push my boat out a little bit and provide some details on that. So to go into a bit more detail on the low band antennas and the high band antennas, to start with the low band antennas, these are basically dipoles that detect two orthogonal linear polarizations just with copper wires and a low noise amplifier, which is situated in these molded heads here in this kind of the electronics inside. And this is all resting on a PVC pipe to stand it up there with some ropes anchoring this to the ground and some rubber springs in the ground to keep it there. So this is what one looks like, very simple, very basic. This is how it responds to signals from the sky. You can see that in a typical observation, this is all bad signal that we don't actually want for our science. This is what we call radio frequency interference. In this case, we've got some that's reflecting off the ionosphere from signals from elsewhere. And you also have the start of interference from the FM band, which operates around 100 megahertz at this end. So we're most sensitive in this part, but yeah. And what I think is really interesting is that all of these elements that I've highlighted here, they're made of cheap materials, right? That are very easy to acquire. So these things are really cheap to build, and we can do this. We can build all of these stations quite cost effectively, and as you'll see, we can do some really high-end science with them. I always thought this is interesting. An old colleague at Sheffield actually described them as coat hangers in a field, and I couldn't argue too much with him. Okay, moving on. So looking at the other part, the other set of antennas, the high band. So these operate towards higher frequencies. These receivers are a little bit more complex. There are essentially 4x4 elements in this sort of mini array. So each of these tiles here has 4x4 elements to collect signals. These all contain amplifiers and their own little beamformers. So it's a little which to decide which patch of the sky, what patch of the sky they can actually see. These things here, that's about 5 by 5 meters. So these are quite big, these tiles. But again, if you look, we're holding our world-leading science equipment in polystyrene structures. The antenna elements are mainly aluminium, and this is just plastic film that's placed over the top to cover it, protect it from the environment. Again, all very cheap instruments, materials to build an instrument with. And this is how the antenna responds across the frequency band that it's looking in. Okay, so changing tack back towards the science side. So Luke gave a nice introduction to AGN. And when we're focusing on what we call radio AGN, which are the ones that have these very fast and powerful jets coming out from their centers, what we need to study the overall impact of these is a survey that has large sky area coverage, is complete. We can detect all the objects we want to, and that we can detect all of the radio emission from these objects. So it needs to be a survey that meets all of these criteria. So this is to introduce how the arrays, a bit more to how the array is structured. We have a dense core of stations in the Netherlands. These are the Dutch stations. There's a core which is situated with the superterp here. It's in the middle of the array. And you have some what we call remote stations that are scattered around the Netherlands that give you longer baselines and therefore higher resolution, which I'll explain a bit more about later. And with just these stations, you can already do a really good and sensitive survey because these are very, very densely packed with antennas that can receive the signal, and they will give you a wide field of view and all the kind of things that you need as long as you cover a big patch of sky. Yeah, I mean, in addition, the LOFAR has the capability of doing even longer baseline observations using these international stations that are spread across Europe, as you can see here. And that's something else I'll talk about. But first, I'm going to talk about this survey that we've been doing with the Dutch stations called LOTS. So LOTS stands for the LOFAR 2-meter sky survey. For this, we're using the higher band antennas, so towards the higher frequency range of the what we can cover with LOFAR. As I said, this is just the Dutch stations, but even with just those, you can achieve a sort of 6 arcsecond resolution on the sky, which is already a lot higher than other surveys. This is a wide area survey. We've got some sky maps here of the coverage. This was up to date as of a few weeks ago, I believe. I got these plots. So in green, for instance, here is all of the ones that have been processed, and blue are observed, and some red ones that are remaining for us to do. So this is the ongoing live status of the LOFAR observations and processing, and you can actually view that here if you're interested in how it's proceeding. At the moment, we have 2 data releases. The first one was only covering, he says, but 424 square degrees of sky. The second one, which just more recently came out, covers around 5,600 degrees squared of the sky, which is around about a quarter of the whole northern sky area. We have, as part of the LOTS survey, observed some deep fields. So these are things that have a lot of data from other telescopes available as well, which means we can combine the information to learn more about the objects that we want to study scientifically, and those have been covered to higher sensitivity than the rest of the fields. So Lockman Hole, Elyson 1, and Bootes. And even across the full northern sky, we have a lot of surveys that have already been done. As Luke mentioned, a lot of AGN and just astronomy in general has been done at optical wavelengths. But we have sky surveys that have been done at infrared wavelengths as well. And we can combine the information from these 2 things with our radio observations. And a thing to note here is that when we say we've observed most of these fields and we've observed them with the Dutch stations, actually they've also been mostly observed with the international stations as well, which means the data exists to do higher resolution observations of the same field, but that requires a lot more processing. so it hasn't yet been done. Okay, so this sky survey probes a region of what we call like resolution frequency parameter space that hasn't previously been observed with other surveys. So there are a few examples of other surveys here. These ones, these three here, NVSS First and VLAS, have all been done with the VLA, the Very Large Array in New Mexico in the US. These are other surveys, some Southern Hemisphere like GLEAM and EMU. But you can see that here at this frequency, no survey has ever resolved the sky so well, essentially, in the radio. And yeah, this sky coverage will increase as the LOTS observations continue and get processed. And this gives us a lot of data to work with. There are a lot of fields in the sky that we can look at, lots of objects. And there are already over 700 science papers that mention LOTS. And many of these actually look at AGN. So what we're talking about tonight, around about 30% have AGN in the abstracts of the papers. Sadly, that means there are probably a few too many to go through tonight, but I will focus on a few highlights that have come out of this survey in AGN Science. Okay. So, yeah, to focus on a few highlights, there's some pretty LOTS images in the background there. So one of the first things we found out is that when you look at large galaxies, so very large galaxies, these ones with above 10 to 10.5 times the mass of the sun worth of material inside them. You know, between 10 and 100 billion stars in them. When you look at these galaxies, you can see that the number that have radio emission increases very strongly with the size of the galaxy, essentially the mass of the galaxy. These lines here indicate different levels of different brightnesses of emission from the radio AGN. And if you go to the faintest ends, so this 21 here, and you go to a stellar mass of just over 100 billion stars, suns, everything is switched on. So 100% of the galaxies at this size have radio emission associated with them, at least at some level. And that's to do with AGN. So these are all AGN, selected to have AGN in them. Okay. So that was a key result. Another thing that we learned quite quickly is with so many images and so many different objects to look at, radio galaxies really do come in many different shapes and sizes. So we had this traditional idea of when you looked at, for instance, the brightest, the biggest, and the brightest radio sources in the sky, we used to think that they fit into two boxes. So you'd have these are called Fanaroff-Riley type 1, FR1, or FR2 galaxies. FR1s are brighter towards the center, then tail off, get fainter towards the edges. FR2s are fainter in the middle and brighter at the edges. And we used to think that this was basically how things were organized. But you can see some of the mess that comes out when you look at the images in detail. So this group here is this is called a mustache galaxy, I believe. It's thought to be because the jet is basically spinning in its axis, precessing, which causes the emission to the jet to change direction, and hence the emission that comes from the jet to also appear in different places. This one's really interesting. This is basically a very fast moving galaxy. So it's kind of moving this direction, you know, and the jets are coming out, but they're kind of getting trailed behind the galaxy because it's moving forwards, right? And so in the turbulent medium, this kind of deflects the jet backwards in the opposite direction to where we think the galaxy is traveling. and that's in a very dense environment of galaxies. And this one here, there's lots of little substructures in here that we think are basically caused by strong variations in the magnetic field. So you can see that there's a lot more for us to think about than putting things into these two boxes when you look at the brightest radio galaxies. So there really is an atlas of interesting objects out there. Before I mention the next highlight, just to sidestep, so Luke mentioned that AGN can have an impact on the galaxies in which they live. And I'm going to focus here on one specific thing that we call AGN radio jet feedback. Feedback that can come from these radio jets. So if you look at a big galaxy that has big jets, outside of the galaxy, in its surroundings, there's lots and lots of hot, very, very hot gas. And when the gas is this hot, it essentially emits emission X-ray wavelengths in order to cool down and to release some of its energy. So this emission of X-ray, which is highlighted in blue here, is basically the gas trying to cool down. When you get a jet involved, you can see that you get these kind of things called cavities, these gaps in the X-ray emission that are co-spatial with where the jet is aligned. So what we think is going on here is that this jet is injecting a large amount of energy into the gas surrounding the galaxy that would normally emit X-rays, and is essentially preventing it from cooling down by that X-ray emission. So it's stopping it from cooling down. And that's important because when gas cools down, it goes on the route towards forming new stars in the galaxy. So if you keep the gas hot, it won't form new stars in the galaxy, or as many new stars in the galaxy. And we think this is important because if you look at all the galaxies that we observe in terms of their brightness, going on this axis here in this plot, and how common they are, you find that if you don't include AGN radio jets and this kind of heating of the gas in your simulations of how this might work, you essentially don't match what you observe. So without a heating source, you get this dashed line, which doesn't agree with what we see. If you include the AGN radio heating, you get something that agrees with the galaxies that we see in terms of their brightness distribution. So this is an important process that acts in the universe that we need to understand. But those are theoretical models, those are simulations. And before LOTS, we had some evidence, but not so much strong evidence that there's enough energy to essentially come out of these jets to do that kind of adjustment in the gas temperature. So some work that was done coming out of the LOTS survey is essentially if you add up all of the energy output that you get per unit volume in the universe from the jets, and you compare it to the amount of X-ray emission you get from this cooling gas per same cubic volume in the universe, these numbers are very, very similar, actually. So these are the same order of magnitude in size. And this provides some suggestion that the total AGN power from these jets is enough to offset this gas cooling, and hence also prevent the gas from forming new stars and galaxies and making too many massive galaxies, essentially the problem here, too many bright. Okay. Yeah, so those are some highlights that came out of LOTS. And for the last bit, I'm going to move on to talk about what we can do with the higher resolution data using the international stations. Oh, sorry, yeah, I wanted to watch that video. So this is a teaser for what we can see. The blobs that you see at the start are what you'd get out of the survey, so the lower resolution survey at 6 arc seconds. And this is what happens when you go to the long baselines and use that extra baseline length to get higher resolution. You start to resolve all these beautiful jet structures that you wouldn't otherwise be able to see. And there are some more teasers around the outside. Okay, so why does this work? I believe you recently had a seminar by Jack Radcliffe, and you've had one from Leo Morabito in the past, so I won't spend too much time on explaining interferometry. But the basic concept is that if you're pointing at a source somewhere in the sky with, let's say, a pair of antennas, you know that if these waves are arriving in parallel, the only difference between the arrival time of the same signal from the source should be this geometric delay. There are other things that affect it outside of the system, but if it was a perfect atmosphere, a perfect uninterfered path towards your antennas, this would be the only delay you'd expect, and that's a geometric, just simple trigonometry time delay that you can work out. So what you do is you essentially can combine these signals from these two antennas, accounting for this delay, together. You correlate them together, and when you do that through some magic maths, essentially, you can go from the signals you receive when you're sampling from different points on the Earth to the image plane, what's actually coming from the sky, brightness, distribution. And this GIF is just showing how this is equivalent to, if you imagine having a big disk, if you were able to have sampled points and just leave the Earth to rotate. So these are the interferometer elements, these points at the start of the GIF. If you let the Earth rotate, or if you do things like move the antennas around, which is what the Very Large Array does, you can fill in a sort of aperture which mimics sort of a traditional telescope dish. And that's what enables you to get the sensitivity to resolution, emission from different scales on the sky. We're mimicking the effect of a very, very large dish that you physically wouldn't be able to construct by combining these signals. And the key thing to note is that the resolution you get out, it can be approximated from the wavelength of the light you're looking at, divided by the length between the baselines that you're using. And if you use the longest baselines, you get the best solution. Okay. And what does this look like for the International LOFAR telescope, which is what we call this network across Europe? So you have the core stations, the super terp and surrounding the super terp, and that gives you a resolution of 500 arc seconds to a maximum of sort of 60, just using that one station. You can go to a bit longer scales where you have more antennas, longer baselines, and this can get to the lots resolution essentially. The one we quote is 6 arc seconds at about 144 megahertz. But if you use the full width of the international array, you can get all the way down to below the ground-based seeing limit in the center of the high band antenna frequency range. So this beats essentially the best you could do from the ground without doing some adaptive optics type techniques with the radio, just by combining these signals from far out antennas. Okay, and this is all based on that principle of the longest baselines means highest resolution. And this is the dish we're mimicking, size of Europe. And what can we get out of this? So when you do this very long baseline interferometry with LOFAR, one thing you can do is you can look at the AGN jet structures in exquisite detail. Before, these would have been sort of blobby structures that wouldn't have been very well resolved. But now with the power of the international stations, you can actually resolve some substructures in the jets. And this particular object is quite interesting, Hercules A. So this is an object that shows these kind of rings of emission, right? You can see them as you propagate out. And if you look at how the emission varies over the frequency range in terms of the brightness you get at different frequencies, you can actually use that to age the source. And if you do that, those rings are actually consistent with the AGN jet essentially turning on and off. So these are representing sort of different phases of the jet's life. So it switched on, stayed on for quite a long time, stayed on, and this plasma was sent out here. At some point it switched off, so there was a gap, and then it switched on again, and the same thing happened. This plasma reached out, then it switched off, etc., etc. So you can see that these AGN have life cycles. You can look at these very, very bright objects as well that are situated in very dense and gassy environments. So lots of gas for the jets to bump into, as Luke mentioned in his talk. This can have some effect. And you pick up on all these kind of structures that we haven't really seen before, and they're actually still puzzling us to this point. Because we've not seen these things in such detail before. You get sort of filaments coming across the galaxy. You can see at the edge, it's a little bit different in the structure towards the center, and these kind of knots and all these kind of detailed parts of the structure that are really interesting to look at. And that's something else that's unveiled with LOFAR VLBI. What you can also do is you can make an image of a very wide field of the sky. So in this case, 7.4 degrees squared. And just basically look at all of the objects sampled in that field and see what we can learn science-wise from them. Look at their morphologies, their sizes, and this kind of information can be used to think about the lifetimes of the lives of the jets and the processes that they might have gone through. And this image that I'm showing here is again another one of these transitioning from the LOTS resolution to the LOFAR VLBI resolution. You can see the kind of structures that you pick up on. And this was our first, one of our first major projects, this wide field image of the Lockman hole field in the sky. And there's some technical details here, but one I'd focus on. Firstly, this image is huge. The full size of the image is 7 billion pixels. And the amount of data you have to collect and correlate, process, calibrate, all these kind of things means that the computing time needed to produce a wide field image at this resolution is very, very large. So in terms of CPU hours, not human hours, because computers can work in parallel, that's 250,000 CPU hours to produce this one image. So yeah, very thankful that computers can do a lot of this for us and work in parallel to put this amount of time down. Yeah. And oh, sorry, I should mention these people are the people who've done the work, and as you might be able to tell from the pictures, they're actually primarily early career researchers, or they were when they did this work, PhD students and postdocs like Luke and I. So this is something that's nice about the LOFAR collaboration. A lot of the leading science in the VLBI area, at least, has come out from Unido people. And this is just to note that we have some more wide field images being made currently because of the challenges of the computing time. this takes a long time, and you have to get all of the calibration right across such a big field. And we have one that's been made of the Elias M1, which is another one of the deep fields that I mentioned, the more sensitive observations we use for these. And we have one that's close to being made. We've had one resolution image at a resolution of about an arc second, and one below that's at sub-arc second resolution on the way. Again, early career people. And I think the last highlight that I was going to show is what we can look, all the previous results were with the high band antenna. This is now the low band antenna. And so this is the extending to very low frequencies below 100 megahertz. And these images here that Christian has produced are the highest resolution images ever made below these frequencies, so in this frequency range. And with the idea that synchrotron emission gets brighter towards lower frequencies, you can get some additional information on the jets from the extra brightness of the emission at these frequencies. And this is kind of an area that we're really just starting to tap into. Okay, so to round up and talk about the future, this image isn't meant to imply that the sun is setting on radio astronomy. This is very much the opposite. We have a lot of stuff that's coming on the way. The SKA, which is something I think Jack will talk to you about, it will be the next big advancement, but I'm going to focus on things that we're doing specific to LOFAR. So the big thing is we're upgrading LOFAR in a few ways to make LOFAR 2.0. Astronomers love awful acronyms. So this one is the digital upgrade for Premier LOFAR Low Band Observing, just so we can make the name Duplo. And what basically is being done is that because the current setup, the back-end electronics actually limit us to only using 48 antennas per station, per Dutch station, sorry, and 96 per international station. But that is only a fraction of the total number of antennas at each site. And so what will happen with Duplo is that we'll triple the computational capacity so that we can use 96 antennas. More antennas means more sensitivity, means we can use all of the LBA, the low frequency, the low band antenna elements at the same time, doubling that, and that means double the sources to use for ionosphere calibration, which is one of the major challenges for observing at this type of frequency. It also means we could do simultaneous high band antenna and low band antenna observations, and it means we can get solutions for the ionosphere, this problem that we have in the calibration, from the high band antenna where it's less affected and we can more easily derive solutions, apply these as a preliminary calibration for the low band antennas, and then do a further correction from there. So there are several advancements that will come just from the simple electronics upgrade. Another thing that will happen is that we'll use a single clock for all of the Dutch stations, single clock timing. And as I kind of mentioned in the interferometry slides, the delay in the sensitivity to the delay in your signal from a source in the sky is really important, because that essentially affects how well you can do these observations, how well the positional information can be used on the sky. And there are all sorts of corrections that, if they're not done, means that the signals from the antennas won't be in phase. So getting a good clock correction is actually something that's important. Wrong times at two stations means a wrong delay. And these upgrades overall will provide around a 5 times increase in sensitivity, and make the images look better as well, the higher image fidelity, an example sort of what we expect the difference to be here. And there are some added bonuses that are included in this upgrade. Will be the raw antenna data can be continuously fed with these upgrades to transient buffers, which means that you can essentially look for things like cosmic ray events, lightning, or transient triggering events 24/7. So we will feed these raw data, everything that's collected, to these buffers, and gives us more data to look through for these kind of transient events. There'll also be more beams in the sky. We can do multiple beams in the sky at once, and that means faster surveys, faster surveying of the sky. So that was what's happening at the stations. In terms of the central processing, we've already got an upgraded correlator for the radio signals from different antennas. This thing basically becoming Cobalt, another acronym that we needed to make. This is already operating, but the thing that will change is that we improved the coding to parallelize the computation and make parallel observations and processing possible. And the achievable speed of transfer from this correlator to the central processing cluster where further things are done will be 100 gigabytes per second. And it's actually this data rate, which is already very high, that will become the limiting factor in this process being streamlined. And there's also a new telescope scheduling and monitoring software being developed. And the final thing we'll add for LOFAR 2.0 is a couple more stations. I've actually already been using these on my plots, I realized, but we're not technically active yet. So we have Medicina in Italy and RAZoom in Bulgaria that will be joining as 2 extra new international stations, give us more sampling of longer baseline stations. And we will be integrating another second super station, so to speak, which is comparable in sensitivity to the core station in the Netherlands, which gives us another good anchor point for calibration, and will improve our observations in that way as well. And this new extension for in Nancy, France, upgrade LOFAR and LOFAR, there's more information available on this site there. In terms of actual research work, our plan is to make a high resolution survey of the sky with international stations. As I touched on, the computation time for processing the international station data is the reason that this hasn't been done yet. But we're currently working on making this a reality. And when it does happen, it will be our first, when it's complete, first subarcsecond northern sky survey. So it will be the first thing that approaches down here. So the Hubble telescope's best resolution, this region in frequency parameter space will be probed, which is well beyond what any of the other surveys have touched before. Okay. There's also something called Weave LOFAR. This is more on the optical side of things. This is a multi-object fiber-fed optical spectrograph. It looks very crazy. It's like this, hundreds and hundreds of these fibers connected to a plate. And I've actually seen this operating in La Palma, and it's just amazing. These fibers all have to move perfectly so that they don't bump into each other to to line up with different galaxies on the sky. And they're a very efficient algorithm to do this, but it's quite a nervous watch actually. But the idea with this is that you'll observe a patch of sky, you put a fiber on each galaxy, which gives you the optical spectroscopic information, the kind of thing that Luke mentioned in his talk. That means we can do lots of other science with them. We can get accurate redshifts, so proxies for the distances to these galaxies that we associate with the radio sources. And it could finally give us some statistics to settle some long-standing questions about different types of radio galaxies. Okay, with that, I'll end here. Sorry for the long summary. There's a lot to get through. LOFAR is basically a phased array radio interferometer operating at these two frequency bands. There's a dense core in the Netherlands and many stations across Europe. We have this sky survey, the LOFAR 2-meter sky survey, which probes a region of frequency resolution parameter space that is not been explored as of yet, and that has hence been very useful for AGN studies, as well as many other things. There are several key results that have come out. We found that the most massive galaxies above sort of 100 billion solar masses, so 100 billion times the mass of the sun, have radio emission from these jets at some level. The total power output of these jets looks to be enough to offset that cooling of gas as we require for our galaxy's evolution simulations to match the galaxies we observe. And there are a broad range of different types, different shapes and sizes for AGN radio jet structures, which question our previous understanding. The long baseline interferometry that we can do with LOFAR has pushed the door open for subarc second resolution studies at low radio frequencies, and this will hence push boundaries for radio AGN studies. And once we've managed to survey the full sky, the northern sky with this, we will have our first subarc second survey of the northern sky. And future upgrades will also improve the sensitivity of LOFAR greatly. And sorry for the pun late on a Friday night, but there is lots more to go. And with that, I'll leave you to ask any questions. Thank you.
Thank you very much, Dr. Pierce. That was most enlightening. Just extraordinary.
Thank you.
We've got time for some questions. And just to kick things going, I noticed there's a question in the chat. Oh yeah, from Martin Kinder. I mean, is there any correlation between the alignment of the BH accretion disk and the plane of the galaxy? Do AGNs exist in elliptical galaxies, or are they only spiral only?
Yeah, that's a great question. I think it came in during Luke's talk, so I don't know.
Yes,
if
it did. Yeah,
Luke wants to speak on that, and I'll cover the other ones. But yeah, I can help if needs be.
Yeah, sure. I mean, it'd be good to get your opinion. I think particularly on the last one. So the answer to the questions, first of all, in terms of there being a correlation between the supermassive black hole accretion plane and the plane of the galaxy, I don't believe there is, at least observed. My impression, at least in the objects I've worked on, is that there definitely seems to be a range of possible angles between the accretion disk of an AGN and the plane of the galaxy. So, for example, the first galaxy I worked on my PhD, in that galaxy, the jets from the AGN are actually going directly into the disk or into the plane of the galaxy. So that would imply that the accretion disk is perpendicular to the disk, so the disk of the galaxy. And in other well-known galaxies, for example, a galaxy called Centaurus A, which I believe is the nearest AGN, we very clearly see that actually the jets are faced out or going directly perpendicular to the disk. So that would imply that the accretion disk and the galaxy disk are aligned. They're in the same plane. So my impression is there isn't necessarily a correlation, but that might be missing something there. And as to the question of do AGN exist in elliptical galaxies or are they spiral only? They do exist in elliptical galaxies. My understanding is we've observed AGNs now in pretty much every type of galaxy. And definitely there are many AGN observed in elliptical galaxies. The most famous of which, I really hope I'm not wrong here because it'd be embarrassing, would be M87, which is a massive, I think, elliptical galaxy, which famously was the target for the Event Horizon Telescope. I think it was the first Event Horizon Telescope observations. That was of the supermassive black hole in the center, an active supermassive black hole in the center of M87, which is a massive elliptical galaxy. I'm not sure if you have anything else to add to that, Johnny.
Yeah, I think you've said what I'd want to say, and yeah, I think the reason that maybe a black hole accretion disk might not be aligned with the rotation in the plane of a galaxy. I think it's hard for us to imagine, but the scales involves this difference in scales between the galaxy rotation, the galaxy scale of a galaxy, and the pinprick of a black hole and accretion disk at the center. It takes quite a long time for things like the angular momentum, so how the disks spin, the information there to be translated to from the galaxy scale to a black hole scale. And indeed, it might not even get down there and translate directly, which is why you get all these misalignments that Luke was talking about. And yes, in terms of elliptical galaxies, we definitely get AGN in elliptical galaxies. And in fact, in the local universe, nearby, relatively nearby universe, a lot of the radio AGN, so the ones with jets, we find those in basically massive elliptical galaxies. So they're actually more common in those elliptical galaxies than they are in spirals in the local universe, at least the jetted types. So yeah, that's something interesting to add. But yeah, I think that's it. You covered everything else.
Yeah, cool.
Thanks. Yeah, Diana's touched on a problem that is amateur and professional radio astronomers fight with, and that's RFI. And she's asking, how helpful will the plan be from Starlink to make their satellites possibly radio invisible? Does this affect you, especially with their downlink feeds, etc.?
Yeah, that would be very helpful. I mean, I think that it sounds quite. I don't know much about the details, but it sounds quite a tricky thing to do because essentially that's how the satellites send their signals back down, right? And radio invisible sounds like quite a goal. But any kind of reduction would be greatly appreciated, at least from us radio astronomers and in other wavebands as well. You know, they do have an effect. We've seen them cause problems in data at various different wavelengths, optical all the way to radio and the other way as well. So yeah, any kind of reduction in RFI is good for us.
I think if I could just tack onto that very, very quickly. So I don't know too much about how the radio invisible thing will happen. I mean, as Johnny sort of implied, I'm kind of skeptical that they will be radio invisible. It's not a great term to use, I don't think, if that's what they're advertising it as. Radio reduction, I'm sure. With regards to the optical, as Johnny mentioned, they're already causing problems for traditional optical telescopes, particularly wide field survey telescopes. The thing I wanted to mention in particular is my understanding is that at least SpaceX with Starlink are engaging with the astronomical community to potentially limit the impact it'll have on astronomical observations. My concern is that over the coming decades, we have many more mega constellations coming from these aerospace companies and governments, and I'm not convinced the majority of them will be willing to talk to us. So I haven't got any direct involvement in this, but I'm slightly pessimistic about the future of these mega constellations and their impact on astronomy beyond Starlink.
Yeah, me too.
Yeah, I think the sad truth is that in terms of impact on numbers of people, it's seen as the satellites are more important than radio astronomy and astronomy in general. So I think that's unfortunately what will tend to rule. But we hope that we can work as much with these kind of companies and get them to reduce any effects they might have on our research. But we'll just
it's a very good point. Of course, I forget sometimes as astronomers that this is very important infrastructure for many people. So it's all a balance, needs to be considered.
Yeah, it's tricky. Yeah.
The life cycle captured my imagination of the AGM. It hadn't really occurred to me. But what kind of time frame are we looking at there?
That's actually a great question. I'm not sure because it's not my work. But I'll go back yeah, so I think this is sort of millions of years type timescales.
Okay, yeah.
So it's not that mean, they could be intermittent on shorter timescales than that, but then you wouldn't see such a difference in the effects. Because if you think about another thing that's hard for us to think about as humans, these distances are absolutely huge, and the distance between here and here, you know, that light probably took millions of years to get between. The particles took, you know, millions of years to get between these two places. So, you know, it could be intermittent on small scales, but I guess we wouldn't even be able to see because it'd just be too. You can get things though that are interesting. That AGN are seen to be variable essentially. This is more on the accretion disk scales where you can actually see that kind of change taking place. But I think things like X-rays, it's better to look at variability. But you know, they can vary on. I think it's timescales of days, isn't it? Even Luke, some AGN. So
yeah, I mean, this is kind of very much an ongoing area. So AGN variability, as we call it, so effectively how fast are the light properties of light from AGN, how fast they vary, what timescales. My understanding from people I know working the cutting edges, this could get down to like, yeah, day timescales, even less in some cases. We have, obviously, Johnny's talked a lot about the state of the art of radio facilities. In terms of optical radio telescope facilities, we have some new survey instruments coming up that are going to observe the sky at very, very rapid intervals. And we think we're going to learn more about AGN variability soon. So, yeah, I mean, we think it could be going down to potentially days. But, yeah, as Johnny mentioned, the turning on and off of AGN is probably on the case of, like, what, say, a million to, like, maybe 100 million years?
For,
like that.
For these jets, yeah, for these
kind
of some things that we're seeing here, I think that's more like millions of years sort of timescales, yeah.
Sorry, Paul. I noticed. Sorry, there was a question from Tony about what bandwidth is using the 2 meter sky survey. Do you know that, Johnny, off by heart?
By bandwidth, you mean the total frequency range covered, or like the fractional bandwidth? Something. The frequency range that's covered is for the 2 meter sky survey. It's from 110 to 240 megahertz. So that's the frequency range we're receiving light from. But if you mean, maybe it means in terms of like the signal data rates and things like that. In which case, I don't know that rate. But yeah, I'm not sure the bandwidth for the actual electronic signals, if that's what he means.
Tony, if you want to chip in and clarify your question, please do.
I can unmute. Yeah. It was when you said 2 meter survey, was that 2 meters plus or minus a megahertz, or plus or minus 20 megahertz or whatever? That was what the question was. But
yeah. So yeah. Okay. So that's been the kind of catchphrase name for it, the 2 meter sky survey. But it's because if you translate a wavelength of 2 meters to frequency, it's the frequency range that we cover. So the 110 to 240, it's in the near the middle of that.
Okay.
So,
thanks.
Thanks for clarifying. Thank you. Yeah.
The other question, if I may, it was to Luke. You're describing the cold molecular gas, 150 Kelvin, kind of doesn't feel that cold. is that because it's being heated? I guess the plasma that's coming out of in the jet is acting a bit like an ejector pump or something like that. So it's like entraining this cold molecular gas, but there must be some heat transfer going on.
Yeah, this is a fantastic question with a lot of nuance. So I'll try and give you a fairly short answer that covers all bases. So first of all, 250 Kelvin, is that cold? Kind of depends who you ask. Just for reference, the stuff that I call ionized, which is like above 10,000 degrees Kelvin, this is stuff that's like above 10,000 degrees, I would call warm, right? There's some people that will call that cold. So it really depends on who you're talking to. For us, considering that we're often talking about gas that's like at least a few thousand degrees in temperature, 150 degrees is pretty cold, right?
Okay.
So that's the first thing. The second question about how is that gas kind of excited, this is a fantastic question. Broadly speaking, there's two potential explanations as to how you are accelerating molecular gas. Okay. So the first, as you mentioned, is what we call entrainment. So this is when the jet will hit the gas and it will effectively just somehow launch all of that gas together. Maybe you have like a bunch of ionized gas which contains some molecular gas in the center, and it all gets launched together, right? I personally don't think that's happening, because you are launching a big, massive, fast radio jet into a bunch of fragile molecules. I can't possibly see how those molecules are going to be gently accelerated. What I think is happening instead, and this is another school of thought, is that actually that jet hits the gas and heats up everything to like thousands of degrees, destroys all the molecules. That then really hot gas is accelerated and starts as an outflow. And then within the outflow, it starts to cool down and reforms the molecules, which we then observe. And eventually those molecules, when they have temperatures of around 150 Kelvin, that's when they start emitting light at the frequency we observe with ALMA. So does that answer your question?
Yeah.
Yes,
Sorry.
thank you. Yeah.
You're welcome. Thank you very much.
It was the energy transfer thing I was interested in.
Yeah, it's a fantastic question. It's one where I'm also very interested in as well. And there's a lot of active research in this.
Okay.
Sorry, Johnny.
Right.
No, I was going to say, in terms of temperatures as well, I think maybe it's better to think in terms of Celsius, because 150 Kelvin is minus 123 degrees C. So it is quite cold, I guess, if you think about it. But yeah, the question about the impact is also a great one, and something that people like Luke are looking into a lot. Yeah.
There's a question from Peter East about where the mass comes from. Presumably that's the mass in the outflowing jets.
Yeah, that would be for you then, Luke, I guess.
Yeah, sure. Effectively, it comes from, the answer is it comes from the gas in the galaxy. So galaxies contain like a lot of gas. I mean, it depends exactly on the galaxy you're looking at, but you're talking about, at least probably 10 billion solar masses of gas in a galaxy. So even if you are bringing like a very small fraction of that down to the center of a galaxy and it gets fed onto the black hole, you don't need much of that. We need a lot, but no, you don't need much of a very high fraction of that 10 billion solar masses of gas to create these jets, right? They're very massive and they're very fast, but compared to the sheer amount of stuff in gas content of galaxies, it's not that much.
Well, I'm going to follow that up with a question of my own. Once it's been ejected, where does it go? Does it sort of fountain out and fall back down again, or does it just keep going?
So again, to an extent, this is an open research question. The broad view is that it will stop. So you'll see, I think Johnny's just stopped sharing his slides, but it's okay. Don't worry, Johnny. As you saw,
I'll bring up something else, but yeah.
Okay, sure, that's fine. So basically, you'll see. I mean, maybe you can enlighten us further on this, Johnny, because I'm sure you know a bit more than I do. These jets have these like jellyfish-like structures at the end, right? We call these radiolobes, and we think that this is effectively where the jets end. And we think this is largely happening because space isn't completely empty. Like around galaxies, there actually is quite a lot of gas that's quite diffuse, but it does effectively have this effect of slowing down these jets. So at a certain point, the pressure that you are imparting into that gas balances with the pressure in the gas itself. So the jets kind of stop. So you can see here, if Johnny's on the right, we have this very well-known object, Centaurus A, and you can sort of see, particularly in the bottom right of that image, you see this kind of like edge to the jet, and that's effectively where the pressure of the ambient gas around the galaxy and the pressure of the jet is balanced, so the jet effectively stops expanding at a certain point.
Yeah, and I was getting this up because you were answering the question about the gas, and because I used this slide for another talk, which I think is quite cool, which kind of dissects a galaxy based on its components, just by showing how if you look at different wavelengths, you can essentially see different components of the galaxy. And you can see that if you look in, for instance, the H1, which is in radio, that's all cold gas. You look at the mid-infrared in the bottom left, that's dust, and then you get other gas at other wavelengths as well, like in the X-rays, all that hot gas I was talking about that emits light in the X-rays. So there's a lot of stuff in the galaxy that you you wouldn't really traditionally think about, because when you look at an optical image, you see the stars. If your eyes were good enough, you'd be able to see things like this, like the dust lane going across. But typically you see, even if you can see a galaxy, it'll be like stars. And yeah, those are the things we think about. But there's a lot of other stuff in a galaxy, and a lot of gas which has a comparable mass to the amount of mass in the stars. So that's all the stuff that gets impacted by the jets and outflows that we were talking about today.
Do we have any more questions before we close the evening? Yeah, maybe not. Well, gentlemen, doctors, thank you very much for a very stimulating and interesting evening. And thank you so much for giving up your time tonight and preparing the work for presentation. I know you're a lot busier than many of us probably. So thank you. Wish you well in your careers ahead of you, and maybe we'll get you back again to update us on new developments on your research going forward.
Thank you
very much.
Thank you for having us.
Thank you very much. It's been a pleasure. Yeah, I've enjoyed it.
If we were in a theatre, we'd all be clapping and stamping our feet, etc.
Yeah, I see enough Zoom applause to make me happy, so I'm good.
Yeah, get that dopamine flowing. Yeah, thank you very much, guys. It's been a pleasure. Thank you.
Okay, yeah. Wishing you well, and everybody on the call. Good night, one and all.
Thanks everyone.
Thanks, guys.
Good night.